everyone.
Good afternoon.
Yeah, my name is Ngosa Kangwa from the lab, SEOB lab. To start with, we'll look at our core keywords and their definitions. So under sampling, we have sample. So a sample is a small but representative portion of a material. And then we come to sampling itself, which is the process of collecting this small but representative portion of a material for analysis. Then we have sampler. These are personnel in charge of collecting samples and preparing them for analysis. And then we have heterogeneous, which is a term that describes materials that are non-uniform in composition and properties. Then we move on to homogeneous. So homogeneous is a term that describes materials that are uniform in composition and properties throughout their entire mass. Moving to the analysis section, we have analyte. So this is a substance of interest in a sample. Then next we have analysis, the process of determining the chemical and physical composition, properties, and concentrations of valuable elements in the material. Then we move on to analysts. So analysts, these are personnel or laboratory personnel responsible for carrying out analysis. Then we have standard operating procedure. So this is a document that contains written directions outlining how to analyze a sample. Then we move on to methods, the next one. So these are means or ways of analyzing a sample for a specific analyte in a specific matrix. And then here we define the matrix as the surrounding material in a sample except the analyte. It has to go through a process called method validation. Yeah, so this is a process where we verify that a method yields correct results. And then we move on to calibration. So calibration is the process of ensuring that a machine is working correctly by mapping the signal to the concentration of the calibration standards. The next word, which is calibration standard. So these are highly pure and well-characterized materials with precisely known concentrations of the target analyte that serve as reference point used to create a calibration curve, which plot an instrument signal against the known concentrations. So here we're talking about a proper calibration curve. So this allows the accurate determination of the concentration of the analyte in a known samples by comparing their measured signal to the established curve. So here we define a signal as an experimental measurement related to the amount of analyte. So this is what we use to make our range of standards for calibration. Yeah, so in the next slide here we have a calibration curve like what we're talking about in this slide here. So we have calibration and calibration standards. So these are calibration standards. Then the next word here we have certified different material. So this is a high purity material with a precisely known certified concentration of a target mineral or element, could be copper or any other element, used as a control sample to monitor accuracy during analysis. Then we have accuracy here. So this is just basically the nearness of a result to the true value. Then precision defines how close results of the same sample are to each other. Then next we have range. So the range is defined here as the interval between the upper and lower concentration of the analyte in a given sample. Then the next word here is the blank sample. So a sample that does not contain an analyte of interest but is identical to the surrounding samples. Then we have decomposition. So this is the chemical or thermal treatment of the mineral or ore sample to break down its matrix and convert analytes into soluble or measurable forms for an analytical determination. Then we have repeatability. Repeatability here is a degree of agreement between independent test results obtained from the same sample using the same method by the same analyst on the same equipment within a short period of time. Then we have reproducibility. So this is the degree of agreement between results obtained from the same sample but under changed conditions. So the laboratory's primary role is to provide accurate and timely analytical results to the mining and processing plant to control production and minimize metal losses. So at SEOB Lab, we also do water quality checks to monitor the environment in case of any pollution. So the lab is mainly comprised of two sections, which is the sample preparation section and the analysis section. For our organizational structure, we have the manager, then we have the sectional chemist, and then we have the senior chemist there, then we have research analyst, who is just basically the same as the senior chemist, but the research analyst here is in charge of the sampling section, and the senior chemist here is in charge of the analysis section. So we have the laboratory analyst there, then we have the assistant laboratory analyst, then we have sample preparation supervisor, then we also have a weighbridge operator, then we have the laboratory clerk, we have the laboratory electrician, we have concentrator, sample preparer, we have so the sample preparation section, an important part of the laboratory responsible for sampling within the plant, receiving samples from various clients, and also preparing the reagents for analysis. So it also includes the weighbridge, which is responsible for weighing trucks that carry material like concentrate in and out of the plant. So the main types of samples received include, so we have plant samples collected from the concentrator plant during the flotation process. And these samples include, we have the main product, which is the concentrate, and then we have the copper ore, which is the feed that they feed into the plant. And then we have the tailing, which is the waste. Then we also have underground mining samples, as well as exploration samples, coming from GOI, Sinomine. In addition, we have dispatch samples, which are concentrates coming from Chambishi copper smelter and the concentrate shed. So these samples are sampled during the loading process. Okay, so when samples are received, they must be checked, they must be verified before preparation for analysis. So samplers, so these ensure that properties such as sample IDs, batch numbers, quantity of sample, testing items, and other necessary information is complete and the same as that on the delivery list, to avoid working on wrong samples or realizing later on that a certain samples are missing. Next, the status of the sample is inspected. So the appearance must be observed, such as whether they are damaged, deteriorated, have any leakages or contamination. So we don't want to work on contaminated samples. If a sample does not meet requirements, it's reported to the sample administrator or the supervisor, the sampling supervisor, and then is not accepted or received until the problem is solved. So this is just a picture of a batch of samples that has been checked and verified, and now is ready to begin working on. So after verifying that the samples are okay, a sample receiving logbook is filled, indicating time received, sample status, as whether it is damaged or in what state, and other information. And both parties, including the one receiving, so the sampler receiving, and the person or the client delivering, must sign to confirm receipt and delivery of the samples. So the samples are now taken through the preparation process, which involves crushing, grinding, mixing, and subdividing. The process begins by crushing the samples using a 150 by 200 big jaw crusher, reducing the sample size to between 15 millimeters to 50 millimeters. So the crushed samples are then packed through a 60 by 100 small jaw crusher, reducing the size further to 2 millimeters. So this is just a picture of the big jaw crusher. So this is a small jaw crusher. This is what a small jaw crusher looks like. At this particular moment it was in use. The samples are mixed evenly, then subdivided by the coning and quartering method as illustrated in the next slide. So this is just an illustration of the coning and quartering method that we use for subdividing and mixing. So a representative sample of about 1 kg is taken, and if it has any moisture in it, it is dried in an oven at a temperature of about 60 to 80 degrees Celsius for 2 hours. Then, after drying, the dried sample is then mixed thoroughly and further split into 2 equal and homogeneous portions. So one portion is put back in the sample bag as a coarse reject. And then the other portion is then mixed thoroughly, further mixed and split further into 2 portions again, using a sample refill splitter or the cone and quartering method. After mixing or crushing, so the sample will be poured on top there and then it will be split. So the other half will be falling on this bucket here, and then the other half will be falling on the other bucket on the other side. So after splitting, one portion of it is packed in a sample paper bag as a duplicate sample. So the pack for the duplicate sample should be labeled with information such as duplicate, the sample code, preparation date, and analysis elements. So elements of analysis could be copper, cobalt. So finally, 100 grams from the remaining portion is obtained and then further milled using a ring mill for approximately 3 minutes and then packaged in another sample paper bag, which should as well contain information such as the preparation date, the sample code, and analysis elements, so elements of analysis. So these same samples, after preparation, the sampler then hands the samples, which is the bag after preparation is done, to the sample supervisor or sampling supervisor, who then prepares check samples for quality control by picking a sample at random per 10 samples of a batch and then obtaining approximately 8% of it and packing it in a separate sample bag, then giving it a unique code. Then the corresponding sample is recorded in a quality control checkbook. Then 2 blank samples and an non-reference standard material is included as well. That's just a picture of samples that are ready to be sent for analysis. Okay, so now we move on to the analysis section. So this section is just as important as the sampling section, as they both work hand in hand to achieve a common goal, which is to produce timely and accurate results for customer satisfaction. So it involves water quality checks, like I mentioned earlier, as well as determination of various elements in ores, concentrates, and tailings. So these are just the few or the common elements we usually analyze. So like I mentioned, for these like iron, manganese, magnesium, lead, silver, gold, cadmium, aluminium, potassium, zinc, we usually do this for in water samples. But for copper ores, we usually we do analysis of copper and cobalt mainly. Under water quality check, we look at physical parameters such as the pH, we do conductivity, we check for total dissolved solids, check for total suspended solids, and turbidity. Then we also test for heavy metal concentration and items such as sulfates, chloride, nitrates, and other potential water contaminants. We move to the analysis of ores. So the analysis of ores, tailings, and concentrates begins with the weighing process. So this is my area of work. So samples are weighed into clean beakers and then decomposed depending on the type of analysis required to be performed. For the analysis of copper and cobalt in ores and tailings, so after complete decomposition, hydrochloric acid is added to nearly dry samples after being cooled. Then the walls of the beakers are rinsed with distilled water and the samples are reboiled to dissolve in salts forms. Yes, so after reboiling, the samples are then cooled and transferred into 100 ml test tubes and diluted to the max. So the samples are then taken to achieve uniformity, then left to settle for about 30 minutes or beyond. So once settled, the samples are then aspirated using an atomic absorption spectrometer. This is just an instrument that we use to detect the element of interest in the sample. So this is just a picture of a colleague weighing the sample into clean beakers. I'm sure you can see the beakers there. After weighing, we add acids and then we wait for them to decompose or to boil to dryness. Yeah, then after drying, we remove these from the hot plate and wait for them to cool, and then we add, there are some other acids that we add also to dissolve the salts after drying. Dissolve the salts and then we wash, and then after washing, we put them back again on the hot plate here, then they'll have to reboil again, and then remove them now for cooling and transferring. So after that, the samples will look like this. I'm sure you can see how colorless they are. They've lost color, so meaning they are decomposed. Now ready to be transferred into these tubes. I'm sure you can see the glass tubes there. We shake them to achieve uniformity. So they have to be shaken and we wait for them to settle. So this is just a picture of samples settling after shaking. And now this is the machine that we use to aspirate these samples. Yeah, so we have to first come up with a calibration curve that will help us now determine the concentration of this sample that he's aspirating, the samples that he's reading, to detect the element of interest. This process is mainly for ores and tailings. So concentrates are analyzed using methods such as titration and electrogravimetry to ensure high precision method determination. So a titration involves reacting a solution of known concentration, which is called a titrant, with a given sample in order to quantify the target element, which is usually copper. So the exact volume of the titrant used to reach the end point is then used to calculate the concentration of the sample. So the end point here in our definition is being defined as the visible moment when the sample changes color due to the presence of an indicator added during the process, indicating that the reaction has ended. Okay, so this is just a picture showing a titration workstation. This is at the end of titration. This one is still blue, and this one is milky white. I'm sure you can see the colors, the difference in color. Then we move to electrogravimetry, which involves the quantitative deposition of metals into a fluid electrode using an electric current. So this is a process known as electrolysis. I'm sure you are familiar with the term electrolysis. So once the metal is fully deposited, the electrode is dried and reweighed, and the difference in mass is used to calculate the concentration of copper. This is just the decomposition process of samples for electrogravimetry. We also use beakers for this. So after decomposition, these samples are dried and then they are filtered. So after filtration, then some other solutions are added and water as well. So after this whole process of filtration and addition of this what we call electrolytic acid, the solution looks like this. We can see. Yes. So after switching on current, the arrangement looks like this. Then I'm sure you can see the color change of the electrons inside the solution. So after this process is done, the solution becomes clear. In summary, to ensure that results are up to standard, certain quality measures are put in place. So this includes sample verification, so where every sample is checked for its correct ID, batch number, physical integrity, like where you check for leakages, contamination, so upon receipt or upon arrival. Then we have a chain of custody where a sample receiving logbook is signed by both the deliverer and the receiver to maintain a clear record of responsibility. And then we have random and multi-quality checking of samples. Then the use of control blanks, which are included among the check samples to monitor for potential contamination during the preparation and analysis process. Then we also have unknown standards to verify the accuracy of the analysis results. Then we have standardized methodology where all analysis and sampling processes follow standard operating procedures to ensure reproducibility and precision. Then also instrument calibration, to make sure that we calibrate our instruments before use to ensure reliability of analytical data. So on an important note, safety is the foundation of every laboratory operation, especially when dealing with machinery and chemicals. So therefore, all laboratory personnel are required to wear full personal protective equipment during operation. So we ensure that strict protocols are followed during the crushing and milling stages to manage dust and prevent inhalation hazards. Then acid fumes are managed using fumes during the decomposition process to ensure a safe breathing environment. Lastly but not least, safety talks are held every morning to inform ourselves of any potential hazard around and to encourage each other to work safely before we commence with our various duties. Thank you. That's the end of the presentation.